In this video, we're going to talk about conditional probability. The probability of an event occurring given that another event has already occurred is called a conditional probability. The probability that event B occurs given that A already occurred is written as the probability of B given A. And that bar that goes straight up and down then is given, and what comes after is the given condition. It is equal to the probability of the intersection divided by the probability of the given condition. So it is always intersection, which is what they both have in common, over the given condition. And the given condition is whatever comes after the bar in the formula. Since we are given that event A has occurred, we have a reduced sample space. Instead of the entire sample space S, we now have a sample space of A since we know that A has occurred. Let me give you an example. What is the probability that you were born January 1st? The probability you were born January 1st is 1 out of 365. Okay, there's only one January 1st in a year. But if I were to tell you that it is known that you were born in January, what is the probability you were born January 1st? Now we know for sure that you were born in January. So instead of looking at all 365 days of the year, then the given condition is that yes, you in fact were born in January. So there's 31 days in January and only one of those will be January 1st. So now my sample space gets reduced. It went from 365 to 31 different days. So right here, this formula is going to become very important as we work through some of the problems. This is the formula for conditional probability. Again, the bar is given, and whatever comes after the bar is the given condition. So notice it's what my denominator becomes, okay? So it's always intersection over given condition. And then one of the things that you have to keep in mind is that the probability of A given B is not going to equal the probability of B given A. If it does, it's just a coincidence, but not necessarily. So we go back to the example about being born January 1st. Imagine if I were to flip it around. So let's say that instead of asking you what is the probability that you were born January 1st, given that you were born in January, which we said is 1 out of 31, let's switch it around. What is the probability you were born in January, given that you were born January 1st? And the answer is 1. If you know for a fact you were born January 1st, then the probability you were born in January is just 1, like you were born in January. And notice that these two things are not equal to each other. So the probability of A given B is not necessarily the same as the probability of B given A. Go ahead and pause the video, take a look at example number 1, see if you can answer those questions by yourself, and then go ahead and press play. Example number 1. The question, do you smoke, was asked of 100 people. The results are shown in the table. What is the probability of a randomly selected individual being a male who smokes? So we're asked about a randomly selected individual. There are a total of 100 individuals. So how many of those are males who smoke? There are 19 males who smoke. So the answer is going to be 19 out of 100. Second bullet. What is the probability of a randomly selected individual being a male? Again, we're looking for a randomly selected individual, but this time being a male. The total amount of males is 60. So the answer is going to be 60 out of 100. What is the probability of a randomly selected individual smoking? In this case, we're interested in, out of the 100 people, how many of them smoke. So these are the ones who smoke. There's a total of 31 out of 100. What is the probability of a randomly selected male smoking? Now this is different because we're talking about a randomly selected male. There are a total of 60 males. And out of those 60 males, how many are smoking? 19 out of 60. So the answer is 19 out of 60. What is the probability that a randomly selected smoker is male? So now I'm looking at all of the smokers. So out of 31 smokers, how many are male? 19 out of 31. Let's take a look at some examples. In part A of number 2, in the toss of a die, what's the probability of obtaining the number 2? Well, in the tossing of a die, the sample space is 1, 2, 3, 4, 5, and 6. There's only one out of those 6 possibilities that is the number 2. Part B. After tossing a die, it is noted that an even number appeared. What is the probability that it is a 2? So this time we want the probability that we get a 2 given that we got an even number. So this means we know for sure we got an even number, so we have a reduced sample space. My new sample space is 2, 4, 6. And then what is the probability I get the number 2? The answer is going to be 1 out of 3. There's 1, 2 now out of 3 even numbers. Number 3. A box contains 2 red cubes and 4 black cubes. If 2 cubes are chosen at random, what's the probability both cubes are red, given that the first cube is not replaced before the second cube is selected? So in this particular problem, we want the probability of picking 2 red cubes, so red and red. In part A, it is without replacement because we are not replacing the first one before going back to pick a second cube from the box. The probability the first time I go into the box that I pick red is 2 out of 6 cubes because there's 2 red ones, 4 black ones. There are 6 cubes in total. And means multiply. So when I take out the red cube, I am not going to put it back into the box. That means that I am left with now 1 red cube and only 5 cubes in total. So the answer is 2 out of 30 or 1 out of 15. In part B, it's also the probability of picking 2 red cubes, but this time it is with replacement. So when you take out the first cube, you're actually going to just put it right back. So the probability the first time you go into the box, you pick red, is 2 out of 6. But remember, you're going to look at it and you're like, oh, it's red. You're going to put it right back inside the box. So the second time you go into the box, the probability you pick red again is the same, 2 out of 6. So the answer is 4 out of 36, which is 1/9. Number 4. 2 dice numbered 1 to 6 are rolled onto a table. Find the probability of obtaining a sum of 5 given the sum is 7 or less. So I need to go ahead and create a lattice diagram. 1, 2, 3, 4, 5, 6. Going down. 1, 2, 3, 4, 5, 6. So right there on your screen, I've drawn for you a lattice diagram. There are 36 possibilities. Now, in the problem itself, we are told that we know for a fact that a sum of 7 or less was rolled, okay? So a sum of 7 or less was rolled. So a sum of 7, 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 6. All of those are going to add up to 7. Remember I told you diagonally, they all add up to the same amount. And if you want, I'm going to put a link to a video where I do talk about the very basics of probability and I introduce lattice diagram and I show you how diagonally they add up to the same amount. So if you want to go back and refresh your memory with that video, but right now, basically, if all of these right here add up to 7, that means that everything that came before has to add up to 7 or less. So if you count the dots, how many of them are there? You would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There's 21 different possibilities now that I'm looking at. I'm not looking at all 36. I'm only looking at these 21 because it is known that we rolled a sum of 7 or less. So that is my reduced sample space. So this tells me that I'm going to have a reduced sample space of 21 possibilities instead of all 36 from the lattice diagram. So at this point, I can go ahead and figure out my answer by finding the probability of getting a sum of 5. So which ones are going to add up to 5? 4 and 1, 3 and 2, 2 and 3, 1 and 4. So there's 4 different ways that I can get a sum of 5, given that we got a sum of 7 or less. So the probability is 4 out of 21. And finally, in question number 5, notice all we have are numbers. So again, the strategy here is going to be to create a Venn diagram. The only difference is right now, I am not given the intersection. You always want to know what the intersection is because it's going to help you create a correct Venn diagram. Instead, they have told me that the union is going to be 0.6. So there's 2 ways that I can do this problem. The first way is to use the addition rule that we learned about, which says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection. So that means basically that if I were to fill this in, I'm going to substitute A union B is 0.6, the probability of A is 0.5, the probability of B is 0.3, so minus the intersection. So that means 0.6 is equal to 0.8 minus the intersection. So what would I have to subtract 0.8 by to equal 0.6? And the answer is 0.2. Another simple way to get this answer is still using your rule, but in this case, I can do it a little bit faster, knowing that I can add the probability of A and B together, which is 0.5 plus 0.3. So I'm technically supposed to get 0.8 for A union B, but I don't. I got 0.6, and that is because I overcounted by 0.2. So eventually, hopefully, you'll get fast enough that you can do it that way. If not, go ahead and use the addition rule. So now that I have that set up, I can create my Venn diagram, which I'm going to need for this problem right here. So I'm going to draw my 2 circles. I'm going to label them A, B, and somewhere in a corner, I'm going to put U for the universe. So now I'm ready to put 0.2 in the intersection. The probability of A is 0.5, so I'm going to put 0.3. The probability of B is 0.3, so I'm going to put 0.1. Add them together. You get 0.3 plus 0.2 is 0.5, plus 0.1 is 0.6, as it's supposed to, because that's what it told me right here. So that means the universe is 0.4. Now we are ready to answer the questions. So for part A, the probability of A given B is equal to the probability of the intersection divided by the given condition. This is the rule that we learned. If we look at the Venn diagram, the intersection is 0.2, and the probability of B, all of B, is 0.3. And then you don't want to leave the number as a decimal mixed as a fraction. So instead, you're going to write 2/3 because I can multiply both of those numerators and denominator by 10 to move the decimal point over. Or you can just divide, and this is going to be approximately 0.667 to 3 significant figures. Let's go ahead and try part B. In part B, we have the probability of B given A. So that is equal to the probability of the intersection, B and A, divided by the probability of the given condition. Here, the intersection is the same. It's 0.2. Whether you have B intersect A or A intersect B, it's the same intersection. The given condition is 0.5. So my answer is 2/5 as a fraction. Or if you divide, it's equal to 0.4. Then in part C, we're looking for the probability of A complement given B. So this is going to equal the probability of A complement and B all over the given condition, which is what comes after the bar, the probability of B. If you look at the Venn diagram, what is not in A and in B at the same time? So what is not in A? So here's A. So what is outside of A and in B at the same time? 0.1. So this answer is going to be 0.1 over the probability of B, all of it, which is 0.3. So my answer is either 1/3 or 2 3 significant figures, about 0.333. So hope this helps with conditional probability. Good luck.